The last part of our look at kinematics is looking at two different kinds of motion. Each are kind of motions that we will see again in the future. One of them later on in this class, and one of them if you were to continue on as a physics major in modern physics, because it relates to relativity. So this first type of motion I'm going to refer to is something called uniform circular motion. We are going to talk about this more primarily. We'll see a little bit of it in our next unit on force, and we'll see a lot more of this when we get to unit 6 on rotational motion. But I wanted to give an introduction to it here because it opens up a whole class of problems to look at in our next unit. So what is uniform circular motion all about? And let's go here to Mathematica by itself. Okay, so what I have here is some circle, and I have some little nugget on this circle, and as a function of time, this little nugget can go around the circle, and it just goes and goes and goes and goes and goes. And if I wanted to, I could have it going at some constant velocity. That's actually what's going on. It has not a constant velocity, a constant speed. I should be more specific. So we've got a constant speed as it goes around the circle. It's set its cruise control, but it is going around a circle. Now, why is this interesting to look at in kinematics? Because if we have some speed and this object is going around a circle, what do we see as the velocity of this particle as a function of time? Because the velocity of a particle as a function of time is changing. So say here at t equals 0, the velocity is pointing up. At some later time, it's pointing up and to the left. At some later time, it's pointing to the left. At some later time, it's pointing down and to the left. At some later time, it's pointing down. The velocity vector is changing as a function of time, even though the speed of the particle is not changing as a function of time. But because the velocity is changing as a function of time, that means that there is an acceleration. That's really what's going on in this problem. So what kind of acceleration do we have? Well, to look at acceleration, we need to see how the velocity changes over some change in time. So what I've coded in is the fact that I could look at some change in time. An initial position and a final position can be different from each other. They're separated by some delta t. And actually, as time rolls along, that delta t is going to be the same. The delta t is the same, which means that these vectors are always different from each other by the exact same angle. This is actually a picture that shows that the speed of the particle is constant, because this separation between the initial and final position for a set delta t is always going to be the same. But if we're looking at the particle at these two different positions, we see that at these two different positions, the particle has two different velocities. If we wanted to see what velocity final minus velocity initial is, well, velocity final is this red vector, velocity initial is this green vector. The difference between them, what we would want to do is add a negative velocity, right? So we take v final, we would subtract v initial. It turns out that what we would get is a vector that points in. V final minus v initial puts us to there. So putting these together, what we really have is an acceleration that points this way. Right? So once again, v final minus v initial, that's this blue vector. That's this blue vector that's pointing directly in. That's what's going on here. So what happens at different instants of time? Over that time interval, the acceleration of the particle is inward seeking. At this other time over here, the acceleration of the particle is inward seeking. So, there's two different kinds of acceleration that we can have. And these two words, one of them is more familiar than the other. There is centrifugal acceleration. Centrifugal means center fleeing. That's what the word means. Centripetal is a similar word, but different. It means center seeking. So what I see in Mathematica here is a center seeking acceleration. Center seeking acceleration is what we see in this problem. And so very often, if we have some particle that's doing uniform circular motion on some circle, the acceleration of that particle, even if it has a constant speed, is a center-seeking centripetal acceleration. Now, when we go into our next unit on force, we're going to see some weird relationship between this. So say, for example, I am in some car and I'm riding around with my friend. I'm in the passenger seat and my friend turns the wheel to go around some corner. I don't feel any force towards the center of the circle. I get jammed up against the outside door. So what I feel is some sort of an influence that's trying to take me away from the center. That's something that's centrifugal. Let's say some of you are more biologically inclined and maybe have done things in a bio lab of some sort that concerns a centrifuge. So what is that thing doing? The centrifuge is not a centripet, or whatever you might call that device. It must be some device that's related to something that is center fleeing, not center seeking. So where does this centripetal thing come from? Why do you say that this acceleration is center seeking? Well, I just showed you in Mathematica what's actually going on. The difference between these two will make a bit more sense when we get to our next unit on force. So I'm going to leave this as a potential thing to look at in the future. However, if we are going to have some center-seeking centripetal acceleration, how big is that acceleration? And what things does it depend on? That's something else for us to look at. So here in Mathematica, I'm just going to get rid of all this other stuff. I'm going to set my delta t equal to 0. And I just reset the whole simulation here. Go back to initial settings. So here I have coded in some velocity. And let's say we were looked at 3 snapshots in time. We'll look at this time, we'll look at this time, and we'll look at this time. And at the first time, we see that the velocity of the particle is up, even though the position is to the right. At time 2, we see that the position is up and to the right, but the velocity is up and to the left. And at time t3, we see that the position is straight up, but the velocity is directly to the left. So we're going to look at 3 different kinds of relationships over here. So I see for position, I initially had some velocity, or some position that was to the right. I'll call that 1. Then I had some position that was up and to the right. I'll call that position 2. And then I had some position that was directly up. I'll call that position 3. All of these positions reside on a circle. And the radius of this circle is apparently a constant. It's always a distance r away. Okay. So going back here, over a certain amount of time, if enough time passes, I get back to my initial position. So there is a special amount of time where the particle travels a distance, the circumference of this circle, in a set amount of time. I'm going to call that time delta t, or not delta t, but capital T. So if I wanted to know the speed of the particle, this is velocity without a vector, so this is just the speed. We see that the particle is going a distance 2 pi r in some special time, t. This is the time that it takes to go all the way around the circle. Especially in the future, times like this will be called a period, but that's totally okay here. This is what's going on with position, and I think we could all agree that that's relatively straightforward. But let's look at the velocity vectors now. At time t1, the velocity is pointing straight up. At time t2, the velocity is pointing up and to the left. At time t3, the velocity is pointing directly to the left. But for each of these times, the magnitude of that velocity vector is always the same. So now we're looking at the velocity. I'm going to say that for time t1, the velocity was pointing straight up. For time t2, the velocity was pointing up and to the left. At time t3, the velocity was pointing straight in, like so. Each of these has the same magnitude of speed. And we see that these vectors are basically transcribing a circle as well. The velocity is certainly changing as a function of time because the velocity was initially pointing up, and then it was pointing up and to the left, and then it was pointing to the left. In an instantaneous sense, while this was a velocity vector, and this was a velocity vector, and this was a velocity vector, this must be an acceleration vector. This must be an acceleration vector. This must be an acceleration vector, and these accelerations are all going to have the same magnitude, right? So here, if I wanted to find out what the magnitude of this acceleration is, this, using similar methodology, must be 2 pi v over that same period. Because if I let that same amount of time pass, the velocities are going to sweep a circle just like the radii swept a circle. This time and this time are the same. Now there's a couple things that we see from this. At time t1, the acceleration is pointing to the left, inwardly associated with the position. At time t2, the acceleration is pointing down and to the left, inwardly from its relationship to the position. At time t3, the acceleration is straight down, inwardly seeking with respect to this position on the circle. So we see just from these two expressions of velocity and position that we have to have a center-seeking acceleration. To go around the circle, I have to have some influence, some acceleration that keeps it on the circle. Now another thing to keep in mind, how big is this acceleration? That's another thing that we could be concerned with. So if we have this relationship for the speed of the particle that depends on time, and we have this relationship with the acceleration of the particle that depends on time, and these two times are the same, well then from the first expression, t must be 2 pi r over the speed, and t must also be 2 pi v over the acceleration. This t shows up here. This t shows up here. And now, because these two things are equal, I see that r over v is equal to v over a. And rearranging terms, this center-seeking acceleration in magnitude is v squared over r. So this is a center-seeking radial acceleration, centripetal acceleration, and we see that the acceleration that is required to stay on the circle depends on the speed of the particle. As the speed of the particle gets big, the acceleration that is needed is very big because it relates to the velocity squared. If you wanted to travel on a small circle, the acceleration has to be very large because as r gets very, very small, a sub r is going to get very, very big. So traveling on small circles requires a lot of acceleration. Traveling at high speeds requires a lot of acceleration. Now, we don't know where this acceleration comes from yet, and that's why I'm pushing a lot of this discussion to our next unit on force, but this is to give us some feeling for how we come about having centripetal accelerations as opposed to centrifugal accelerations. How we know that acceleration is center-seeking, we saw this in Mathematica, and we saw this just by relating positions and velocities on some circular relationship. But we also see how big this center-seeking acceleration is. So that's useful. We will see more problems associated with that in the next unit. And there is one in the notes on Canvas if you're following along, and that's totally fine. But I'm not going to dwell on it now. We're going to see it a lot more in the future. What I'd rather do is spend a bit more time on another related topic, which is something called relative motion. And to bring that up, for the topic of relative motion, I have a little page here that's sort of put together. And in the book, it looks at the topic of a train. And maybe somebody is walking along the aisles of a moving train. And the person is walking at a typical speed of, I don't know, a meter per second. That's a typical kind of walking speed. Maybe a little bit slow, maybe a little bit fast, depending upon the walker, but it's certainly something that's realistic. And so this person is walking along the train aisle, and if they were walking past somebody that's sitting on the train itself also, sitting in some seat, that person sitting in the seat would see this walker walking past at 1 meter per second. Great. Now the question is, what would somebody outside the train see for that walker? Because the train is moving at some speed, and the walker is moving with respect to the train. So the combination of the walker moving with respect to the train and the train moving with respect to the ground means that the speed of the person with respect to the ground is not 1 meter per second squared. Certainly not if the train is moving. So whether you're at the station looking at this walking person, or you're sitting on the train watching this walking person, you see different things. Does that mean that reality is different? No, no, no. It all just depends on your frame of reference. Everybody is allowed to have their own meter stick, and everybody is allowed to have their own stopwatch. And anybody that has a meter stick and a stopwatch has a particular frame of reference. And maybe something that's a little bit more intuitive, because not a lot of people here in South Florida ride on trains, is just driving around on I-95. So let's say we have a car rolling along at 80 miles per hour in what used to be the HOV lane, which is now the express lane, and I'm moving at some different speed. I'm one lane over from them, and I'm going 75 miles an hour. So both of us are moving at a pretty high rate of speed. If we were all to drive past somebody that's sitting on the shoulder, the person on the shoulder sees that one car in the formerly HOV, currently express lane, going at 80 miles an hour. But me, One lane over going 75 miles an hour, I don't see that. I see the person creeping up on me at 5 miles an hour, or moving away from me at 5 miles an hour. So depending upon whether we're in the side of the road or we're in some other car, we don't agree on what we see for the speed of that person. So we need to figure out, how do we put all of these moving pieces together? And one way to look at this is graphically. Let's say there is some agreed upon reference, point A, and there's going to be some point P that's some distance P with respect to A in the problem. This is just some vector. But what I'm saying is this black vector represents the position of P with respect to A. Okay. Well, knowing how vectors add together, we could also look and add another point, point B. And one way for me to get from point A to point P is along this straight line, RPA. But another way for me to get from point A to point P is to go from point A to point B, and then go from point B to point P. So there's going to be two vectors that could work the same way as that first one. The position of B with respect to A, and the position of P with respect to B. Both of these things are going to do the same thing. They're describing the same thing because of the way that vectors add. Now I'm going to change the problem ever so slightly. And we're going to say that point B is allowed to move. It's going to move at a constant velocity, but that constant velocity can be in any direction. So this point B is going to be moving at some speed v of B with respect to A. So I'm always going to be able to determine the position of B from point A and how it changes as a function of time. And because of that, what we have is some relative motion. If B is changing its position with respect to A as a function of time, how this person at point B sees point P is going to be different than how somebody at point A sees point P. So say, for example, I was sitting in some car at the side of the road because I'm that person on the shoulder, right? Okay. Now, I look over and maybe I see somebody else. They're sitting on the other shoulder and they're also at rest. Okay, that's totally fine. So somebody like me at point A can see point P, and point P is always sitting at the same place. Fine, great. But if I wanted to see how somebody in that express lane is seeing that other person, I need to first move to the frame of reference of that person in the truck. And that person in the truck is moving fast really, really quickly. But that person in the truck looks at that other person on the other side of the road and sees not the person going forward, but the person going backward. So I see the truck moving, say, northbound. The truck sees that other person on the side of the road moving southbound. The speeds are the same, but the directions are completely different. I see it going back, whereas so me at point A, I see the truck moving forward. The person in the truck sees me moving backwards, moves out seeing that other person on the other side of the road moving backwards. This is what relative motion is about. We see different things. We don't agree on that. But there's nothing that says that we can't both be looking at some particular P that's doing something else, that's moving and doing different things. So here in these notes, I say that if we wanted a position transformation equation, it looks a little bit like this. If we wanted to see how the velocities relate to each other and how we see different things in terms of velocity, we could take the derivatives of both sides of this position equation. And if we wanted to see how everybody agrees with acceleration, okay, well, we could do that as well. But what do I mean by the analysis of point P? So we have this position, and we have this way of looking at all of the different parameters. But what we said is if I wanted to know the position of point P with respect to point A, I need to know the position of point P with respect to B, and I need to know the velocity of point B with respect to A and the time. So this is a constant velocity situation. This allows point B to move in any direction at constant velocity with respect to point A. Now, what is point P's position as a function of time? Well, that is going to be r, the position of A with respect to position of P with respect to A, its initial value, plus the velocity of P with respect to A's initial value times time, plus 1/2 the acceleration of point P with respect to A, t squared. This is what a position vector looks like with constant acceleration. So here we're looking at cases of constant acceleration of point P with respect to A. Similarly, r P sub B is going to be r P sub Bi. So I'm going to call this RPA, RPB is RPBI plus V PBI T plus 1/2 A P sub B T squared. And now if I was to put these expressions up here, I see that basically this thing can go in here, and this thing could go in here. Now this allows point B to move in any direction at constant velocity with respect to point A. But another thing to keep track of, point P with respect to anything must have constant acceleration. Must have constant acceleration. Okay, well, some related things are looking at velocities, right? I'm going to call these velocities u instead of v because we've already used the v variable in a couple of different places. I'm going to say that the velocity of point P with respect to A is going to be the derivative of RPA with respect to time. And I take the derivative of this box with respect to time, and I get a V PA initial times time plus A PA T. This is no T here, sorry. Similarly, U PB. I look up here, I take the derivative. This is going to be V PBI plus a PB t. That's where this velocity relationship comes from. If I take the derivative of both sides of this equation, I see that u PA is equal to u PB plus v BA. So B is moving with respect to A, P is moving with respect to B. We at point A would see something different because it's the vector sum of both of those things. Okay? Now, what if I wanted to take the derivative of both sides of this? A PA is going to be d of u PA dt. And what we see is, yeah, that's what it is. I take the derivative of this. The only thing that's left over is a PB. But if I go here and I take the derivatives of both sides of this, VBA is a constant. That's what we were saying up here. Point B is moving at a constant velocity with respect to point A. So here, if I wanted to define the derivatives of both sides, I'm taking the derivatives of these two things. And what this tells me is that regardless of whether we sit at point P, point A or point B, we see the constant, acceleration of point P exactly the same. So we can be sitting at rest with respect to the ground, and we're watching point P go through some system with constant acceleration. I can watch a projectile motion problem from the ground. If I was to watch that same projectile motion problem from a bike that's rolling along at 10 miles per hour, as long as my speed is constant with respect to the ground, I will see that projectile motion problem in exactly the same way. I will see the exact same constant acceleration. I might see weird things with velocity. I might see weird things with position. We won't always agree on that, but we will always agree that the only acceleration that that particle is feeling is g straight down. That's what this is saying. So what is said to be an inertial frame of reference, we don't know what inertia is yet, we're going to talk about that next time, is we can be in any frame of reference that is not accelerating. As long as we are in a frame of reference that is not accelerating, we can look at anything else and we're all going to agree on how that other thing is accelerating. So going back to one note here quickly, what we eventually see is that different people in different frames of reference moving at constant velocity may see position differently. We could disagree on what velocities are. That's totally fine. But we all have to agree that acceleration is the same. Acceleration is working the same way. There's way more details that go into this particular section that maybe don't relate to getting ready for an exam. This is the underpinning of relativity, how different observers see different things. And so as you move into modern physics, this is a great place to start and figure out what's going on. But the way we construct it doesn't require anything with relativity. So as an example, what we're really doing here is saying that if I want to know, for example, how a plane is moving with respect to the ground, I first have to know how this plane is moving with respect to the air and how the wind is blowing. How is the air moving with respect to the ground? Putting these two topics together allows me to figure out how the plane is moving with respect to the ground. And depending upon the direction of the wind, for the exact same plane, with the exact same propeller speed, trying to do the exact same thing, if the wind is blowing in different directions, the plane is doing different things. Maybe something more familiar to us living in Boca. Many of you possibly have boats or have been around boats before. Depending upon the direction of the current, your boat is going different speeds with respect to the earth, with respect to the ground. If you're moving downstream, you can move much faster than moving upstream, which is a different speed altogether than trying to cross the river. And let's say I did want to cross the river. What direction do I point my boat so that I get to the dock on the other side? Because if I don't account for the speed of the current, I'm going to end up downstream if I point right at the dock. So I need to figure out how to paddle upstream so that the current will take me back to the place that I want to go. These problems, whether you're in the airplane or whether you're on the boat, are relative motion problems. That's really what they are. So in the interest of just looking at one example, there are a couple of examples that are already worked out in the Canvas shell. There are some that are in the notes already. But I wanted to look at one in particular. And because this is related to a modern physics course, or often related to a modern physics course, this is actually a problem from a modern physics textbook to get us thinking about relativistic phenomena. But this is all nice and non-relativistic. Surway is actually an author of a very respected set of introductory physics textbooks. I could have been using Surway for this course, and actually this is what I learned with Surway and Jewett. So many of these notes are inspired by Surway's work, but this is actually from his modern physics text. In this problem, we're told that we have some airplane, and it's flying upwind, downwind, or crosswind. And we would like to see how long it takes to go these different directions. Okay, so if, for example, we have wind going at some speed v, and I would like to get from some point on the ground to some airport here, but my airplane moves maybe at some v of the plane with respect to the air. This is velocity of the air with respect to the ground. This is how I could figure out how to move my plane, with respect to the ground. So the velocity of the plane with respect to the air plus the velocity of the air with respect to the ground tells me the velocity of the plane with respect to the ground. And we want to move some particular direction. For example, we will move straight north in this problem. Okay, so the speed of the plane with respect to the air, I'm going to just call that v. We're later told what v is, but this is this is the speed of the plane with respect to the air. We're told that this is c. The speed of the air with respect to the ground, the wind speed, we call this v. So if we know the hypotenuse of this triangle, and we know this opposite side of the triangle, this magnitude is c squared minus v squared under a square root. That's how fast the plane is moving with respect to the ground, vectorially speaking, right? So we really have to get from some airport 1 to some airport 2. They are really on the map. And if it's a windy day, I have to account from the wind so that vectorially I end up at the correct place. Pilots have to account for the wind by flying at least with some component upstream. But these are how the speeds relate to each other. The speed of the plane, speed of the air, speed of my motion with respect to the ground. Okay, so now let's say this distance between airport 1 and airport 2 is L. If I wanted to find the time it took to get from airport 1 to airport 2, time 1, this is going to be L divided by this speed. So meters divided by meters per second, miles divided by miles per hour, is some time. Okay. Now, what if I wanted to fly from airport 2 back to airport 1? How long would that take? It would take the exact same amount of time. Because while the triangle is flipped over, there's a mirror image of the triangle is exactly the same. So we have this. And if I wanted to find the total time to do this, these two things times 2, that's how long it's going to take to fly from airport 1 to airport 2 back to airport 1 on this day. Now I'm going to do one additional thing. I'm going to factor out a factor of c squared from this. Here, and then pull that c squared out of the argument of the square root. Like so, which can be written as 2L over c, 1 minus v squared over c squared to the minus 1/2 power. So with this orientation of wind, airport orientation, and direction that I need to fly, this is how long it takes. Now obviously the thing here in parentheses is dimensionless. A speed divided by a speed doesn't have any units, 1 doesn't have any units. Everything here is unitless. But meters divided by meter per second has units of seconds. So this really is a time. Now what if we wanted to do the problem a slightly different way? Let's put this aside. What if we still had the same two airports? Let's use this pen. We'll use consistent pen. So we still have airport 1, airport 2 here. We still have airport 1 here. We still have, we're going to have the wind going in a different direction. So now we're going to do the upwind and downwind. So let's say that the speed of the wind is this way. So we could actually have our airplane moving at c upwind initially. These two speeds are going to add, and if we have our plane going at speed c with respect to the air, and the air is moving at speed v with respect to the ground, when we're going from airport 1 to airport 2, the time that it takes is going to be this length L divided by c plus v. Okay. Now, let's say it's the same windy day. And we still have the wind going at v. But now I want to fly from airport 2 to airport 1. Now the speed of my plane with respect to the air is this c, but the speed of the air with respect to the ground is this y. My velocity is going to be v minus c. In terms of its direction, it's going to be going down, but it's not going down as fast. If I wanted to know the relative speed with respect to the ground, it's going to be c minus v. That's how fast it's really going. 500 miles per hour south with respect to the air, but the air is going 100 miles per hour north with respect to the ground. So the plane is moving at 400 miles per hour south with respect to the ground because of that relative motion. And so if I wanted to find the total time here to go from airport 1 to airport 2 and airport 2 back to airport 1, it's going to be L 1 over c plus v plus 1 over c minus v. We want to get a common denominator. So that would be c minus v plus c plus v over c plus v, c minus v. So I multiplied c minus v on top and bottom here. I multiplied c plus v on top and bottom here, which gave us c plus v, c minus v as the denominator of both of those things. But then I had a c minus v and a c plus v that I was adding together with that common denominator. V and v cancel out. This is 2lc over c squared plus cv minus cv minus v squared. C squared minus v squared. Okay, well, I'm going to do something similar to what I did before. And factor out this c squared. 1 minus v squared over c squared, but then I have this c and that squared cancel out. So here, the total time is 2l over c, but now we have 1 minus v squared over c squared in the denominator. So let's compare these two things that we found. When we were flying upwind and downwind, we found this thing with the units of time, 2l over c, but we've got this thing in parentheses to the minus 1 power. It's a 1 minus v squared over c squared, but it's to the minus 1 power. When we were flying perpendicular to the wind on a different windy day, we still have this 2l over c factor, but this is not to the negative 1 power. This is to the negative 1/2 power. This is different. These two times aren't the same. Depending upon how the wind is blowing, we're going to get different results. And we think to ourselves, well, gosh, when the wind is blowing with us, we are able to go fast. But that trip coming back is worse. We're getting hammered as hard as we possibly can on the way back. Now, if I'm flying perpendicular to the wind, it's the same problem going both ways. I'm never really able to go as fast as I possibly can. But, okay, which of these is bigger? Which of these is smaller? And which is a better configuration to have if we have to do round trips? And that's when we get out our calculator, right? So we've got our calculator here. we're told that V in the problem is 100 miles per hour. We're told that C is 500 miles per hour. And we are told that L is 100 miles. So using our calculator, let's look at this scenario first. V squared over C squared is going to be 100 divided by 500. That's a ratio, but I have to square it, right? Squared. This is being subtracted from 1. So we've got this. Now this is going to be to the minus 1/2 power. To the 0.5 negative is equal to this. It's some number that's bigger than 1 times 2 times L is 100 times 100 divided by C. Is equal to 0.408 hours in terms of the units that are given here. If we wanted to turn this into minutes, so this is 24.5 minutes. Okay, let's do the same thing over here. This is the other one we have to do yet. So again, we have V squared over C squared, or V over C, quantity squared. So 100 divided by 500. This, not times. Good, I caught that. 100 divided by 500. This quantity needs to be squared. It's going to be subtracted from 1. But this is to the minus 1 power. So it just gets flipped over. Now this is going to be multiplied by 2, multiplied by L, and divided by C. This is 0.417. Different number than before. Let's turn this into minutes. 25 minutes. These two times are not the same. Those aren't the same times. So we see that on a windy day, it is advantageous for us, if we're doing round trips, to make sure that we're moving perpendicular to the wind and not upstream and downstream of the wind, because we can actually do the flight faster. We can distinguish between which direction the wind is going in our travel times. Now, some other things that we can concern ourselves with here in this problem: how did the pilot figure out which direction he needed to go in order to account for the wind and make sure that he moved directly north? Well, he's using trigonometry here, right? Because he knows this speed and he knows the hypotenuse. If he wants to figure out the direction he needs to travel in order to calculate some theta, theta is going to be the inverse sine, in this case, of V over C. Why? V is the opposite side, C is the hypotenuse. So we have our calculator here. V divided by C, 100 divided by 500. Inverse sine of that is 11.5 degrees. And this is 11.5 degrees west of north. This is how the pilot figures out which direction he needs to go. Maybe we wanted to know, how fast is the plane moving with respect to the ground? We can look at that as well. C squared, 500 squared, minus v squared, 100 squared, is this. I take the square root, 490 miles per hour. That's how fast the plane was actually moving with respect to the ground. Now this is different than what we saw with this problem, right? So here we could have had c plus v, which is 600 miles per hour. We could have c minus v for a speed, which is 400 miles per hour. But this average speed is always higher, which is why you can do the travel in less time. That's how that works. So over the course of this hour or so, not quite an hour, fortunately, we've tried to look at a couple of different types of motion. We've looked at uniform circular motion that requires a centripetal acceleration in order for the particle to stay on the circle, but we've also looked at how different observers can observe the motion of an object with uniform acceleration from different frames of reference, different configurations of constant speed, and we all agree on some of the physics and how we can do problems related to boats, how we can do problems related to airplanes by just basically doing a little bit of vector math. I hope this was useful. Good luck, everyone.